Hello, students. Welcome to Chapter 6. As we can see from this first slide, Chapter 6 is involving inverse functions, and eventually we want to be able to solve trigonometric equations. So this first section of Chapter 6 focuses on the idea of inverse functions for all of our trigonometric functions: inverse sine function, inverse cosine function, etc. And that's a big topic, and that's a lot in here. So we're going to begin today in this video by just focusing on a review of inverse functions, just this first part, inverse functions, and try to cover a lot of the aspects of inverse functions that was originally introduced typically in Algebra 2 or something like that in the past, but it's very challenging for students to understand. So let's start with the review of that, and then we will, in future videos, apply that to the idea of producing an inverse sine function, cosine function, etc. So what is an inverse function? So let's first begin with the idea that we have a function of some sort and remind ourselves what it means to be a function. So the loose definition of a function is that it's a relation between x values and y values, and the x values are called the domain and the y values are called the range. And the relation is such that each x value has only one corresponding y value. And normally we have function with like a function notation, f of x, and then we'll have a formula for the function. So let's say we had x squared. Now, excuse me, when we're using the f of x notation, it already implies that we have a function. But we did have a way to see if a graph of x and y values as points formed a function. It was called the vertical line test. So we could imagine that applied to this x squared function, which we already know is a function, but let's look at the x and y values for this function, or just a few of them certainly. And so if I plot like 0 gives me 0, 1 squared gives me 1, 2 gives me 4. If each case I take the x value and I square it to get the y value, and we use some sort of nice simple whole numbers or negative numbers as well. -1 squared is 1, -2 squared is 4, -3 squared is 9. Then we get this table of x and y values, these pairs of values that we can plot. 0, 0 is the origin, then 1, 1 is this point. 2, 4 gives me another point. 3, 9, 5, 6, 7, 8, 9 gives me this point. And then I have those values for -1, -2, and -3. And then we get the graph by imagining that all the intermediary values could be connected if we connect the dots here. And hopefully this parabola has some familiarity or memories from your past of studying parabolas and things like that. All right, so as a reminder, if you're just looking at a graph of pairs of values of points or something like that, or maybe you even have an equation with x and y in it, you can recognize you're looking at the graph of a function if it passes the vertical line test. And the vertical line test basically said, if anywhere I make a vertical line across the graph, it will only contact the graph at one point. And it doesn't matter where I make that vertical line, but any vertical line would only cross the graph at one point. So that was the vertical line test. And if a graph has that property, passes the vertical line test, then we know it's a function. Because what that means is that each input x value only corresponded to one y value. When you make a vertical line and seeing that it only crosses, oh, that's not very vertical, and see that it only crosses once, what that means is that that x value only corresponds to one point on the graph. So this is going to help us because we now want to consider the idea of taking each of those values that we had as results. In this case, all these squares that we got, 1, 4, 9. So these were the results. And remember, these are from the range. If you take all possible outputs of a function, all the answers that you can get, we call that the range. And all the inputs were called the domain. But the idea behind an inverse is you take some range value and the inverse tells you what the original input was that gave you that. So for example, let's say we focus on a 4. The question would then be, what did I square to get 4? So what an inverse function is trying to do is it's trying to take the answers of the original function and tell you what the original inputs were that got that answer. So in the case of the squared function, if you have the answer 4 was the result of squaring something, the inverse function wants to tell you, well, what was it that you squared to get that? And so you may recall that the inverse of squaring ideally is square rooting. And so the square root of x function is supposed to help us determine what we squared in the first place to get that number. And if I tried to apply that to a 4, I would say, well, what is the square root of 4? And I would get 2. And then I could say, oh, that shows me that originally I squared a 2, and that's how I came up with a 4. So that's the idea of an inverse function. And this square root function, which is again introduced back in algebra, has the goal of creation that we can then take the square root of squares and see what was squared in the first place. That we want to undo the squaring function, and what undoes squaring something is square rooting it. We want to say, if I had something that was squared and I then square root that, what I get is what I started with, whatever I squared in the first place, because this is a way that we isolate the x variable when solving equations. This is the way we get back to original values, things like that. So this is a pretty complicated thing. And originally when people learn square roots, they just start remembering square roots. Square root of 9 is 3, square root of 25 is 5. You take perfect squares and you think of what was squared to get those. But there's actually quite a lot of complexity here. And so the first thing I want to point out, because it ends up being very relevant to our work when we try to apply this to trig functions, is that actually, if you look at this graph of the x squared function here, it is a function, but as it stands the way I've graphed it here, actually it does not have an inverse function. The square root of x function is supposed to be the inverse of squaring, but actually it's not. You have to modify the original function of squaring things. You have to mess with it in order to come up with this inverse function. And we want to be able to talk about that. So let me see why we have an issue with this. So the way I can point this out is that when I say, what did I square to get a 4, I ideally should take note of the fact that also if I square -2, I get a 4. And so that really, if we say, what did I square to get 4, we would have 2 possible results. You could say it was -2 or +2. Either one of those could have been what we squared to get a 4. There's a way you can see this by looking at the graph. The y value, remember, are the output values of your function. They're the range values of the function. So when I'm saying that what did I square to get 4, I'm choosing the y value of 4. So if I draw a horizontal line where all of the y values of 4 are on that line, this is the line where y equals 4. If I draw that line and we can take a look at where that line crosses the original x squared graph, what we'll see is that it crosses it in two places. And that's because there were two numbers that we could square that would end up with a 4. And we could trace those back down and we could see, yeah, we squared a 2 and that gave us a 4, but we also squared a -2 and that also gave us a 4. And so what that means is if we are trying to start with the 4 and then go back to what you squared in the first place, there's two possible answers. And the problem with that is that if your input of 4, if you begin with a 4 and that corresponds to a 2 or a -2, the problem with that is that's not a function, because that input of 4 has two outputs. And what that means is that this graph doesn't actually have an inverse function. That's the problem. So let's think about this as trying to imagine creating a table of values for my inverse. And how would I do that if I have multiple choices? Well, the way that the square root function decides to fix that is it defines the radical symbol, the square root symbol that we usually use. It defines that not just by being any square root, but by being the positive square root. The positive square root. If you say that this symbol only refers to the positive square root, well then when you say what positive number did I square to get 4, that eliminates the negative possibility. That takes away the -2. So then I can make a table of values where x is the number that I squared and the square root of x that's positive is the positive number I squared to get that. Then when I put in a 4, the only possible choice is a 2. Then when I put in a 9, what positive number did I square to get 9? That must have been a 3 because we're not considering the -3 value, etc. I can then say 1 is a 1, square root of 0 is 0, even though that only has a positive value. But of course, I never get those negative numbers that were squared in the original graph to get those same answers. So what we do basically to allow this inverse function, the square root function, to be created is we define the square rooting process to only be for the positive numbers and no negative values are considered. And sort of what that does graphically is it says, well, when I'm looking at the parabola, I'm going to not consider all of the negative x values on the graph. I'm going to eliminate that part of the graph. You can imagine that if I eliminate that part of the graph, let's even just take it off of here. If I eliminate this, well then, for example, when I have my y equals 4, it doesn't connect on the left and the right side. It only connects on the right side. If I eliminate all of those values, then this horizontal line of the y equals 4 only hits the graph in one place. And then that one place that it hits the graph, we go down and we see, oh, well, x has to be a 2. And so imagining a horizontal line intersecting a graph and needing it to only intersect once instead of twice so that we can have an inverse function, that creates a test. So this creates a test that's like the vertical line test for a graph, but now it's a horizontal line test. And basically, if you can imagine a graph not intersecting any horizontal lines twice, but only once, then that passes what we call a horizontal line test. Horizontal line test. Hopefully this sounds familiar. I never know whether students had a chance to really look at this well in algebra or not. So basically, if you're going to create an inverse function for some existing function, if you think about what the existing function looks like graphically, it needs to pass a horizontal line test for an inverse function to exist. It needs to be that any horizontal line would only hit the graph once, because then that horizontal line's output value, 4, 5, 6, whatever it is, whatever that value is for the horizontal line, each of those output values for the original function correspond to only one input value for x. And then you can say what that original x value was in the function that you started with that gave you that answer. In the case of the squared function, I can say which x value did I square to get 7, for example, and when I go back and trace it down here, I would end up getting the square root of 7. And only that value would be the number that you squared to get a 7. So I can put in a 7 on my function, and square root of 7 is my answer for my inverse function. Each input now has only one output. And what we see is that the domain of the original function, all the values that were in the domain of the original function, except the ones we threw away, are now the range values of the inverse function. What were the x values in the original function are now the y values in the inverse function. So the domain becomes the range for the inverse, and the range of the original function, the numbers that were the answers to the original function, the perfect squares in this case, those become what you start with in the inverse function. So the range becomes the domain in the inverse function. So in this case, we know the function that we're looking for already. We have this square root of x, and then we were introduced to that in algebra as the inverse of squaring something. And this can, if you think about it graphically like this, it allows us to make some simple statements about the relationship between the inverse function and the function that you start with. So for example, since all of the x values of the original function become the y values and vice versa, you can look at each individual point of the original function. So let's say I look at the 3, 9 point here, because 3 squared is 9. And that is going to correspond directly with the reversed x and y values of the inverse function, 9, 3. X was 3, then y becomes 3. Y was 9, then x becomes 9. So that for each point over here where you had an x value and you had a y value, when you go over to the inverse function, that's going to switch over, and the y value will now go to the left, and the x value will go to the right. And so remember, the left values are the domain, and the y values are the range. And so that's why the y values of the original function were the range values, now become the domain values of the inverse function. And you can imagine this going on graphically. So for example, if I plot the point 3, 9 on my crowded graph, let me clear up some of this space. Certainly I can clear up all this stuff. If I go back to my original graph and see where the point 3, 9 was, actually maybe I'll use 2, 4 because it's a little bit easier to work with. Okay, so if we look at this point specifically, 2, 4, let's focus on that. Here's the point 2, 4. And that was on this spot over here. Well, that translates over here to 4, 2. If you switch x and y, you get 4, 2. If I graph 4, 2, that's here. So what you can imagine is that for each point on the original graph, to go to its corresponding inverse point, you would simply switch the x and the y values. And if you do that for every point on a graph, what you can imagine is that the point basically gets flipped across this diagonal line. This diagonal line is the line where y is equal to x, 1, 1, 2, 2, 3, 3, 4, 4. That's the line y equals x. And basically this point just hops over to the corresponding point on the other side. The point 1, 1 is actually on the line, so it doesn't move. But let's say I go now up to 3, 9. Here was 3, 9. And if I go straight across, 1, 2, there's where I hit the line. 1, 2, come out the other side, I'll be over here. So if I flip to the corresponding point on the other side of this diagonal line, that's that 0.93 on the inverse function. So if I take every point on the right part of this x squared function and I flip them over that diagonal line, I get all the points on the inverse function, so that the entire sort of right arm of the parabola, if I flip that over the line or reflect that over the line y equals x, I get the inverse function. And what you'll see is, therefore, this is the graph of the square root of x. And if you graph the square root of x on a graphing calculator or in Desmos or anything like that, you will see that it's like one branch of the x squared parabola that just, instead of going up, now goes off to the right because it gets flipped or reflected across the line y equals x. And this helps us to sort of make a simple connection between a function and the inverse of that function. Again, as we start applying this to sine, cosine, tangent, things like that, I think this will help simplify, at least mentally, what's going on if you think about it graphically. That all the x and the y coordinate values of points on the original function simply got their x and y values switched, and graphically the graph just got flipped or reflected around the diagonal line, and that helps us connect original functions with their inverse functions, certainly at least graphically. Okay, so it's a lot to absorb here. There's a lot to think about here. Let's go ahead and move forward with the slide presentation of how they review inverse functions and see if my example of from algebra of square root of x being the inverse of x squared helps us get through some of these. All right, so moving forward, I'm going to maybe use this later when we look at some trig functions. But they begin, as I have, by just reviewing the idea of what it means to be an inverse function. So it says, recall that for a function f, every element x in the domain corresponds to one and only one element of the range, which is the y or the f of x value. And so I'm going to just point out from our discussion above that what this means graphically. Graphically, this means that the graph of the points in question for this f passes the vertical line test. So when they say every element x in the domain corresponds to only one element y in the range, what they're saying is that every vertical line for each x value only hits the graph once. And that's what it means to pass the vertical line test. So then they turn right around and remind us that if a function is defined, if the original graph that you're looking at, so that each range element is used only once, what that means, each range element is each y value is used only once. That means is hit only once, that the graph only hits each y value one time. That would mean that for every horizontal value fixing all of the y's at 5, you would only hit the graph once. So what this means is that the graph passes the horizontal line test. So if a graph passes a horizontal line test, meaning every horizontal line only hits the graph once, then we call this a one-to-one function. And one-to-one functions means that it has an inverse function. So the vertical line test, when you apply that to a graph, tells you that the graph is a function if it passes. And the horizontal line test, when you apply that to the graph of a function, tells you if that function has an inverse function. And so going back to our parabola, when the parabola originally had two arms going up, it failed the horizontal line test. And so by basically eliminating the left half of the x squared function, by saying I'm not going to consider x values that are negative. I'm only going to consider positive numbers that were squared to get that. We then, eliminating the left arm, got a graph that passes the horizontal line test, and therefore the square root function exists for that side of the graph only. And so the thing I want to point out here of how that was done back in algebra, even though it wasn't explained that way, but this is how we will do it now in trigonometry, is that you eliminate the repeating values of x for answers by restricting the domain of the original function. So what we did by eliminating all the x values is we basically said we're only going to consider x values that are greater than or equal to 0, and that was a restriction on the values you could plug in for x, and that's a restriction on the domain. And so that's what we're going to do with our trig functions as well. We're going to restrict domains to then have a function which we can create an inverse for. So that's why we want to consider that in this case. So being able to pass the horizontal line test is needed to come up with an existing inverse function. And to do that, you sometimes eliminate parts of the original function's graph and restrict the domain until you get to the point where it passes a horizontal line test. So that's what's going on here. Passing the vertical line test means it's a function. Passing a horizontal line test means you can then, an inverse function exists. All right, so here they're reminding us or pointing out that the inverse function of a one-to-one function, meaning that it passed the horizontal line test, is defined by taking all the x and y values from your original function and switching the x and the y. And so they're doing that here. They're saying we're going to say that the inverse function is equal to the points of the original function with all the x and the y's flipped. So in the original function, you plugged in an x, and then that gave you a y value. Now in the inverse function, you take that answer in the y value, and then we're going to go back and give you the x value that we started with. And we know that only one of those exists because this is a one-to-one function, so there's only one x value that we can use. Now we're also going to remind us that there's this special notation for an inverse function. And they're going to note that. Is that on the next slide? It is. So notice this is not exponential notation, not a power. The -1 is not a power here. So let's look at how the next slide points that out for this notation, even though I think it, yeah, the notation is a little bit off. The -1 in the f to the -1 is not an exponent. And so what they were showing here is that when you have that -1 notation in between an f and an x in f of x notation, that this is not the reciprocal of f. This is not 1 over x. So the reason that we're saying that in this case with this notation is that when we've put a -1 up there like a little superscript before, it was a power. It was a -1 power. So for example, if I have 5 with a little -1 written up there, that is an exponent. And the definition of a negative exponent was that you have the reciprocal, that you flip it, that would be 1 over 5 to the +1. In general, we had a definition that x to the -n is equal to 1 over x to the +n. But this is when you're talking about having an exponent, having exponential notation. And what they're saying is that in the case of f with a -1 on it, that is not exponent. That's why you do not flip it upside down. So let's see how this makes sense in our square root notation. So for example, if f of x is equal to x squared, then note that the -1 notation is referring to the inverse of the x squared function. And again, to have an inverse, we had to throw away all the negatives. But when you do that, you then get the square root of x function. Whereas if I have x to the -2 power That's what you need for the notation to have 1 over x squared. Because here, that's an exponent. So the minus on the 2 as a power on an x gives you 1 over x squared, but the minus 1 on the function notation for x squared gives you the inverse of the x squared function. And so basically, you'll just get used to seeing that when you have a minus 1 up there to the right of an f notation, that it is not an exponent. You don't flip it. That's not a negative exponent. That simply is a notation that refers to whatever the inverse function would be. And that we have to keep in mind because that's a mistake students make often when they're first getting into using inverse functions a lot. They keep thinking that maybe they flip it or something. All right, so now we have a bit of a summary of some of these key points. And I tried to use the example of x squared and the graph of x squared to illustrate a lot of these things they're describing here. So let's see if hopefully we can summarize these in a way that makes sense. So first of all, in a one-to-one function, each x value corresponds to only one y value. So that part there, each x value corresponds to only one y value. That means it passed the vertical line test. And that's why it's a function. But to be a one-to-one function, the and part comes in. So not only that happens, and each y value corresponds to only one x value. That part means that it passed the horizontal line test. So when you have a one-to-one function, it's not only a function, vertical line test, but it's also one-to-one, horizontal line test. And when both of those things are true, if a function is a one-to-one function, then f has an inverse function. And that -1 notation is used for inverse function. And so we're going to need to have this to happen graphically. I'm having us focus on it graphically because that's how students are able to wrap their minds around this. If you're trying to look at a function, like if I look at the sine function, we know it's a function. You can think about the wave of a sine function and you can say, yeah, that passes the vertical line test. But you can also think about the sine function wave and realize that a horizontal line test are going to hit those bumps a bunch of times. That's going to fail a horizontal line test. And we're going to have to work with that before it can be a one-to-one function and have an inverse. We're going to have to modify that function. All right, so that's what they're discussing here. And that's why we want to have these ideas in mind in order to take these concepts and then apply them to trig functions. Now, again, when you do this, when you have a one-to-one function and then you have an inverse function exists, then it reminds us the domain of the original function is the range of the inverse and vice versa. And so when you switch the x and the y's of all the points, then all the points that were on the left then move to the right, and all the points that were on the right switch over to the left. And that's why the domain and the range switch for the two. And specifically, if you think about what that does to the graphs of f and f inverse are reflections of each other across the line y equals x. And you could see that happening point by point. I think I might have erased that. No, it's still there. Nice. You can see that this reflection happens point by point, like the point 2, 4, switches over to the point 4, 2, and that's a reflection across this line. 3, 9 switched over to 9, 3. And then if you do that for every point, that translates, getting dizzy, to the idea that the graphs of the two are reflections of each other across the line y equals x. The line y equals x is the 45-degree diagonal right between the x and the y axis. All right, so that's the summary of sort of the idea and the properties of functions and their inverses, how they relate to each other, and what you need to have about an original function in order to then come up with an inverse function. So in the next slide, they review an algebraic process, typically introduced in Algebra 2. And so let's review that. So if you want to find a formula for the inverse function, we're not talking about graphically anymore, but a formula from the original function, that you possibly could try to go through these steps. And now this would have worked originally in algebra. It doesn't work with our trig functions or anything. So let's review this, but this won't actually give you a way to come up with the inverses for our trig functions. So let's say, as an example, that we had an original function f of x that was equal to, I'm going to say 2x plus 5. So you may recall this is a linear function, so we could think about it graphically. We could imagine that it passes the horizontal and vertical line tests, that it does have an inverse. But this process is focusing just on formulas. So in step 1 of this process, if we wanted to find f inverse of 2x plus 5, what we would do is replace f with y. So instead of f of x, we would write y. And then we would interchange the x and the y. So we were just saying that all the points of the original function, like 2, 4, get switched to 4, 2, that you switch the x and the y's of each point on a graph. Well, you can do that in the formula too. So what we'll do to exchange these is we will switch the x and the y values in the equation formula. And so then we would have that x is equal to 2y plus 5. And when you make that switch with the x and the y variable, you are now looking at the equation, which when graphed would give you the inverse function. So this is an equation of the inverse function. So then to come up with the formula of f inverse of x, we then need to solve for y. So in the next step, we want to solve for y. So I would, let's sort of remember mathematically what we would do: subtract 5 from both sides. And that would give me that x minus 5 is equal to 2y. And then I would divide both sides by 2. So then I would end up with the fact that x minus 5 over 2 is equal to y. So then now that is our formula for the inverse function. So we simply would replace y with our new inverse notation formula notation. And so that means that x minus 5 over 2 is the formula for the inverse function to the original function that we started with. So that's step 3. So this works nice if you have an original formula for a function, and if you're able to undo all the things that were done to x. So in this case, x was multiplied by 2 and 5 was added. So we subtracted 5 to undo adding 5, and we divided by 2 to undo multiplying by 2. And if you lump all that together on the other side, you get the formula for the inverse function. And then the inverse function will undo everything that the original function did, taking you from the answer back to the original value for x. Now, of course, we can't do that with a sine function or a cosine function, because we don't get our answers for those with some algebraic steps, some algebraic operations. We have to look up values on a circular, on a unit circle or something like that for the circular version of the functions, etc. However, this is reviewed here, and this reminds us that the idea in the end is that the inverse function undid all the stuff the original function did and takes you from the answer of the original function back to the value you started with for x in the first place. So this little review sometimes helps students keep that in mind. And so if you put all this together, they do have a nice graphical slide here to remind us what this translates to. That each point of the original function, a, b, gets translated to the flip or reflection of that point across the line y equals x, b, a. You just switch the values. If you do that for every point of the original function, then you end up flipping the entire graph of the original function or reflecting it across the line y equals x. So they have a nice example here where the original function was x cubed minus 1. And we could go through those steps on the previous slide, steps 1, 2, and 3. We could add 1 to both sides and take the cube root to get rid of the cube power, and then you would get this formula for the inverse function. However, you can also just look at the graph of the original function and see that if you take the entire graph and reflect it across the line y equals x, you get the graph of that inverse function. So all of these aspects of taking an original function, modifying the domain if you need to, so that you end up with a one-to-one function, then reflecting that across the line y equals x, or flipping all the x and the y values of all the points, then gives you this inverse function. All of these aspects of the relationship between a function and its inverse and how to get from one to the other, we're going to be sort of looking at all of that and applying that to sine, cosine, and tangent. And so the first thing they start to do is consider the inverse sine function, but it's a lot at this point, and this video is already long enough. So I wanted to stop here where we simply did a review of the notion of inverse functions in general. And with that in mind, we'll think about that, reflect on that, and in the next phase of this introduction, we'll apply it to trig functions. So for now, try to think about those aspects of inverse functions, maybe even practice some problems a little bit, and we'll stop there for now. Keep up the hard work, and we'll move on in the next video to trig functions and their inverses.